which would be of the form phi 1 times k1 plus phi 2 times k2 plus phi 3 times k3 plus phi 4 times k4. And we would have to take the Hamiltonian, we have to take a 4 by 4 Hamiltonian to write an effective shorter equation for these coefficients. So now we have a 4 by 4 Hamiltonian that we'd have to diagonalize instead. There's a 2 by 2 Hamiltonian because now all of a sudden we're mixing 4 states instead of just 2 states. If you were in 3 dimensions, you have a cubic Brougham zone boundary, in which case the 8 states in the corners could all mix into each other. In 2 dimensions, you could have a triangular lattice, in which case 3 could mix into each other. The general rule is always in degenerate perturbation theory, whichever states have the same energy and can be connected to each other by a reciprocal lattice vector, you have to handle them all together and write down an effective Hamiltonian for that subspace of states. So that's the only added complication. So now we're actually going to look at some real data, real materials. Does anyone ever read the examiner reports? Yeah. Is it required that they have to make nasty comments? Is that really, do they get that instruction? I mean, I have to sympathize with them because being an examiner is actually a really hard and unpleasant job. But boy, so what I'm going to show you is a problem that came up on an exam a couple years back, and the examiner made some really particularly unkind comments about it. Absolutely no one actually managed to get it right. That's why I'm discussing it here. It's a hard problem. Anyway, so we're going to think about an FCC system. So this is the Brougham zone of an FCC system. Remember, it's the same shape as the Wigner site cell of a BCC lattice. There's this truncated octahedron shape. And the material in particular we're going to think about is silicon carbide. It has this crystal structure, this so-called zinc blend crystal structure that we've seen before. So silicon is at 0, 0, 0, that's the yellow atoms, and carbon is at 1 quarter, 1 quarter, 1 quarter, that's the blue atoms. So we've seen this before in, what was it? We looked at gallium arsenide, I think. Exactly the same crystal structure. Silicon carbide, incidentally, is an important modern semiconductor. We replace silicon in a lot of high-powered devices for certain reasons. Anyway, so here we have, that little thing? We have a nice dispersion here drawn, and you can see how they've plotted the dispersion as a function of various directions in the Brougham zone. So gamma equals 0 is the definite, the letter gamma always means k equals 0, the k equals 0 point. So then they'll plot things like gamma to x. So this is taking a cut of the excitation spectrum along the line from gamma to x, that's plotted here. And then from gamma to k is plotted here, and gamma to L is plotted here. So you're taking basically cuts through the Brougham zone along these various lines and showing the various energy bands that happen to be there, or the eigenstates. Now you can kind of see here what's going on. The gamma to x is more, well, gamma, it's k equals 0. So you see this parabola, this nice parabolic spectrum around gamma, the k equals 0 point. And you can see here, what was going to happen is these two branches were going to intersect, just like we had here. That this was going to be a free electron band, where two bands, the first band and the second band, were going to intersect, except that they opened up a gap because of the periodic potential. Is that clear? That's, at least morally what was going to happen here. These two were going to come together, and then they opened up because of the they opened up this gap because of this periodic potential. Is that, yes? Okay. So you can see that happening at the x point, you can see that happening at the L point, and so forth. So you see, I mean, there's a lot more complicated stuff going on in this picture, but you see that general physics of gaps opening up at the Brougham zone boundary. Notice that x here is right on the Brougham zone boundary. All right, for the price of a chocolate bar. At the x point, what is the reciprocal lattice vector in terms of Miller indices that's being scattered by?
0.
Good guess, but not right. Also good guess, but also not right. 200. Very good. Yeah, it's 200. The reason it's 200, you remember that for an FCC lattice, the smallest reciprocal lattice vector is actually 2, 0, 0, not 1, 0, 0. Because in order to be a reciprocal lattice, it has to be a family of lattice planes, and if you had chosen 1, 0, 0, you would have missed the points in the middle. Another interpretation of the same statement is that there's a selection rule for FCC lattices, which is that all indices have to be even, or all indices have to be odd. So you don't have a Bruin zone boundary for 1, 0, 0, you only have it for 2, 0, 0. If you wanted to go through the whole, the harder way of seeing this, you could actually sit down, start with the primitive lattice vectors of the FCC lattice, calculate from it the primitive reciprocal lattice vectors of the FCC, the primitive reciprocal lattice vectors, and then you could figure out that that x point to the opposite x point is the distance 2, 0, 0. Okay. All right. So now we're going to switch the story here, and instead of looking at silicon carbide, we're going to look at silicon. Morally, it's extremely similar, silicon and silicon carbide. They look like the same crystal structure. We've only replaced the carbon at 1 quarter, 1 quarter, 1 quarter with another silicon at 1 quarter, 1 quarter, 1 quarter. It's the same structure as diamond. And you notice exactly the same structure, except there's no splitting at the x point now. Why not? These are really good. Think hard.
Not an FCC.
Because no, it's still FCC.
Same potential.
With what?
Same potential.
Not quite. No. Good. These are all good guesses, but they're not right. I'm going to eat that one. All right. Yeah, this was a question that no one got right, so it's a hard question. So what it tells you, the fact there's no splitting, it's telling you that v sub 2, 0, 0, the Fourier component in the 2, 0, 0 direction is actually 0. Now, why would that be? Well, let's remember, when we tried to calculate the Fourier component of a potential, what we actually did was we converted it to, the Fourier component of potential is actually the same thing as the structure factor, right? That's the Fourier transform. The Fourier transform of the potential is actually exactly the same as the structure factor. And that has in it this S basis term for silicon at 2, 0, 0. It will be sum over some form factor for silicon. Form factor for atom alpha in the unit cell, alpha in the unit cell. E to the I G dot R sub alpha. Okay? So for silicon, it's the same form factor for both silicons. One silicon is at point 0, 0, 0, so that just gives you 1. And the other silicon is at point, let's see, so it's 2, 0, 0 is HKL, and the other silicon is at point 1 quarter, 1 quarter, 1 quarter. So this thing here is minus 1. So in fact, the structure factor of the basis ends up being 0. Another way of saying it is the reason that you don't have any Fourier component of the potential at 2, 0, 0 is because you get perfect destructive interference of the wave from the silicons at 0, 0, 0 and the wave from the silicons at 1 quarter, 1 quarter, 1 quarter. So there's no scattering by this reciprocal lattice factor in silicon where there is in silicon carbide because the structure factors, the form factor F is, if the form factor were different for the two terms, then they wouldn't quite cancel. Okay? Good? It's a rather subtle point, but it's very general. And to prove that it's very general, we're going to look at the vibrational waves, and we're going to see exactly the same physics. So for vibrational waves, for phonons, okay, chance to redeem yourself. How many phonon branches should there be? How many phonon modes should there be for silicon at every point in the first Bruin zone?
3?
No. 6, who said that? Yeah, good. You get it after this, yeah. I can't throw that far. Yeah, 6, because there's 2 atoms per primitive unit cell. Each one has 3 directions of motion, so that makes 6 degrees of freedom. Oops. Okay, so here it is. These are the phonon spectra for silicon carbide and silicon, and you can count there are 6 branches, 1, 2, 3, 4, 5, 6, in each of them. 1, 2, 3, 4, 5, 6. Now you may notice in some regions it looks like there's only 4. 1, 2, 3, 4. And that's because 2 of them have come together and have exactly the same energy along certain branches. So it's hidden that there's an extra branch. But here they're all shown differently in this region. It has to do with, you happen to be looking along certain symmetric directions, so two of the energies come exactly together. Notice that there's 3 acoustic branches that come down linearly to the gamma point. That's k equals 0. Those are the acoustic branches, and then 3 of them are optical. They don't hit 0 at k equals 0. And notice you have exactly the same physics going on. For pure silicon, these 2 branches come together and they don't split. Whereas for silicon carbide, they're split. It's exactly the same physics. There's no scattering by the reciprocal lattice vector 2, 0, 0 in pure silicon because of this this type of interference between the two scattering components. All right, good, good. All right, Let's move on a little bit. So, where should I start? Over here. So we pretty much described how band theory works, give or take, and now we have to start thinking about filling up bands. And there's some important principles we learned about filling up bands with electrons. And the first important principle that we determined before is that for n unit cells in the system, there are n k states in a Brillouin zone, or in a band, times 2 spins, equals each band holds 2n electrons. So that's the first important principle. So you can have a situation, I'm sort of again drawing this in more or less one dimension. Here's the Brillouin zone. You could have a band like this, another band up here like this. And if you have an even number of electrons per unit cell, so if even number of electrons per unit cell, then you could fill a band. So for example, you could fill up, with 2 electrons per unit cell, you could fill up this entire band, then there could be a gap to the higher band. So if filled band plus gap, then we have an insulator. And the reason it's an insulator is because there's absolutely no freedom to move those electrons around unless you overcome the gap energy. And the gap energy can be quite large, so it takes a certain minimum amount of energy, this energy, to take an electron out of this band and move it up to that band. Assuming that doesn't happen, the band has to be completely inert. It can't hold heat, it can't carry current, it can't rearrange itself at all. The thing is an insulator. If the gap is kind of small, so an insulator with a small gap is called a semiconductor. And we'll discuss those quite a bit more in the next couple lectures. But it's called a semiconductor roughly because the gap is small enough that at room temperature, for example,